Okay, last page. We have a table here, and it says this is calculator active, so we do get to use our calculator. Let's pull that up, and we can clear out all of this stuff. Don't need that anymore. So it says let f be an increasing function defined for x greater than 0, and the table above gives values for f. So the function g is given by, so f and g are different. F is given as a table, and g is given as an equation. So the first question is, well, might not need a calculator yet. Let's find out. So the function h is defined by g of f of x. Find the value of h of 2 as a decimal approximation. So h of 2 is going to be equal to g of f of 2. So we just got to figure out what these values are. So f of 2, so when x is 2, f is 8, so this is going to be g of 8. And then g of 8 is going to be equal to 8 as I plugged everything into here. So that'll be 8.25 minus 2 to the 8 minus 6. So 8 is what I'm plugging in. There's my function, which is 8 minus 6 is 2. So we get 8.25 minus 2 squared, which is just 4. So 8.25 minus 4 is 4.25. And we don't even need a calculator for that one. But you can always plug it into your calculator just to verify that we did it correctly. Okay, find the value of f inverse of 40, or indicate that it is not defined. So reading f inverse, I don't have an f inverse table. So instead, one thing I like to do just to make things, so f of 40 equals some number. We'll call it, I don't know, call it n. And I need to get 40 by itself. I'd rather read this as f. So 40 is equal to, and I'll just take the f function of both sides. So 40, because those two cancel out, is equal to f of n. So when is the y value 40? Is what this is asking us. And the y value of f is 40 right here. So n is going to be 32. So f inverse of 40 is 32. Okay. Find all values of x as decimal approximations for when g of x equals 4. Okay, so again, we're given g of x, so g of x is the function, is the expression. So I need to know when 4 is equal to 8.25 minus 2 to the x minus 6. So start by subtracting 8.25 from both sides, and you end up with a negative 4.25 is equal to negative 2 to the x minus 6. I still have to get rid of this negative first before I do anything else, so let's multiply both sides by negative 1. So I get 4.25 is equal to 2 to the x minus 6. Now I got to get rid of that base, so I'll take the log base 2 of both sides. So log base 2 of 4.25 is equal to x minus 6. And then last, I will add 6 to both sides. So log base 2 of 4.25 equals x. Now notice I did not stop to type anything into the calculator that entire time. I'm not going to do that till the very end. That way I know it is as accurate as possible. So let's bring up the calculator and we can type this in. It is log base 2 of 4.25 plus 6. Oh, I forgot a plus 6 here. I'm going to write that in. Plus 6. So plus 6. And so our answer is 8.087. So x equals 8.087. There we go. Determine the end behavior of g as x decreases without bound. So the limit is what we would say of g of x as x decreases without bound, so as x goes to negative infinity, is, and so we can plug this into the calculator real quick. Oh, I kind of forgot to hide the calculator. So we said here that the limit of g of x as x approaches negative infinity, so that is the end behavior of g as x decreases without bound. We can type this into our calculator. So we have g of x I can't see over there. Let's see here, is equal to, what was it? It was, where'd it go? 8.25. 8.25 minus 2 to the x minus 6. So here we can see as x, oops, wrong screen. We see here as x increases, or as x decreases without bound, this is approaching some number. It looks like it's getting really close to 2.25. We can go down here a little bit further just to verify. But yeah, it looks like it's x, the y value is hits a cap at 2.25. So this will be 2.25. So now we've expressed our answer using mathematical limit notation. Awesome. Okay. Use the table of values. Wait, hide the calculator again. So now we're going to use the table of values of f of x to determine if f is best modeled by a linear, quadratic, exponential, or whichever. So we need to go back and enter f into our calculators. So I might not need that again, I'm not sure. So we will just hide this one for now. And I will create a table. On top is 2, 4, 8, 16, and 32. And then these numbers are 8, 16, 24, 32, and 40. And then to figure out what model is best, we are going to create a regression line. So let's try a linear regression line, and we can see that has an r squared value of 0.871, which is just terrible. So we're definitely not going to do linear. The next one is quadratic, so we can check quadratic. That has 0.98 isn't terrible. And next one we're going to try is exponential. Exponential has an r squared of 0.78. That's definitely not one we want. And then we'll try logarithmic. And logarithmic has an r squared value of 1. So it is exactly logarithmic. So we will hide this. So use the table of values to determine the best model. And it is best modeled by a log function. Give a reason for your answer in part C, based on the relationship between the change in output values of f and the change of input values of f. Okay, so in this case, they don't want us to talk about r² value. They don't want to talk about regression lines. What they want to talk about is what is the relationship up here. So as we can see here, this is times 2 from there to there. From there to there is times 2, times 2, times 2. So every time they are adding, they are multiplying by 2. And then here, this is plus 8, this is plus 8, this is plus 8, and so on. So the x values are increasing proportionally. I think they want you to use that word, proportionally. The x values are increasing proportionally. We can be a little specific and say with a common ratio of 2, and the y values are increasing in a linear fashion. Something along those lines, with a common difference of 8. So they're increasing by 8 every single time. Oh, I'm kind of off the page there. So they're increasing by a common difference of 8 every single time. And so that concludes all our the videos. So let me know if you have any questions, and I'll see you tomorrow in class.